So in the last class, we formed a table for 3 and 4 valve conduction mode. So we got the expression for Vd and the voltage across valve 1 for all the 12 subintervals. So if I want to know the voltage jumps, see, the purpose of knowing voltage jumps is to ensure that the thyristor valves are rated for the required dV by dt values. So if I try to look at the, so I will not again rewrite the table. So I will just uh, say what are the different subintervals in which I get the different expressions for voltage across valve 1 and directly write the expression for voltage jump. So if I take alpha to alpha plus u minus 60. So there are many subintervals where the voltage across valve 1 is 0. So we have in the first subinterval 0, second subinterval 0, third subinterval 0. Then in the fourth subinterval it is minus 3 by 2 EV, then 0, then 3 by 2 EA, then 0, then minus 3 by 2 EC, then 0, 0, 0, 0. So if I want to know what are the voltage jumps, so we see that there are how many jumps? 1, 2, 3, 4, 5, 6 jumps. So from here to here, here to here, here to here, here, this one, and finally this one. So the expression for these 6 voltage jumps, so I'll directly write the expression. So what you need to do is take the value of take the expression for voltage across valve 1 and substitute the appropriate value of omega ot. You will get the voltage jump. So I need to take, for example, the first voltage jump is minus 3 by 2 EB evaluated at alpha plus u. Then the second jump is 3 by 2 EB evaluated at alpha plus 120. So if I try to take these expressions and substitute the appropriate values of omega ot, so I will get these expressions for voltage jump minus root 3 by 2 V sine alpha plus u plus 30 degrees. That is the first voltage jump. So I will leave it to you to verify this. The second voltage jump is sorry, 3 by 2 V sine alpha plus 150 degrees. Then 3 by 2 under root V sine alpha plus u minus 150 degrees. Then root 3 by 2 V sine minus sign, minus root 3 by 2 V sine alpha minus 30 degrees, minus root 3 by 2 V sine alpha plus u plus 30 degrees, then root 3 by 2 V sine alpha plus 150 degrees. Now we also formed a more detailed table with a column for VD as well. So from the column for VD, which gives expressions for VD in the 12 subintervals, we can get the average value of VD. So if I want to find the average value of VD, so it is denoted by uppercase V with a subscript D. So what I can do is I know that VD repeats after every 60 degrees. So I have to just take the expression for VD for the first interval. So in the first subinterval it is 0. So I have to just take the expression for VD in the second subinterval. So it is 3 by pi, which is reciprocal of pi by 3. So I am just taking for 60 degrees. So in the second subinterval, which is from alpha plus u minus 60 degrees to alpha plus u, sorry, alpha plus 60 degrees. The expression for VD is minus 3 by 2 EC d omega OT. So what you need to do is just substitute the expression for EC and integrate and leave it to you. I will again leave it to you to verify that this is equal to root 3 by 2 VDO cos alpha minus 30 degrees plus cos alpha plus u plus 30 degrees. So this is the expression for VD. Now in the last class, we got the expression for ID in terms of IS alpha and u. If you recall, we derived this equation. So I will just rewrite that equation. ID is IS by, say, of course, the last step I didn't go through all the manipulations. I am asking you to do that. Yeah. By the way, I just want to let you know, whatever I have asked you to do so far are all simple ones, except the expressions for the fundamental and harmonic component for the DC side voltage and the AC side current in the case of 2 and 3 valve conduction mode. So only those are laborious. All others are, something which can be done in just a few minutes. Okay. So only if you look at the 2 and 3 valve conduction mode, the fundamental and RMS expression for the AC side current and the RMS value of the harmonic, the fundamental and harmonic component RMS of the AC side current and the RMS value of the harmonic of the DC side voltage. These two are a bit laborious. All others are straightforward. Okay. So one should be able to do it in just a few minutes. So this is IS by root 3 cos alpha minus 30 degrees minus cos alpha plus u plus 30 degrees. So what we do is we try to again get these expressions for VD and ID in terms of gamma instead of alpha. We have defined an angle gamma. I also said why we defined that gamma. See, gamma is actually called extinction angle, and which happens to be the commutation margin angle for normal inverter operation. Okay. So if I want to write this instead of gamma, what is gamma? Gamma is nothing but 180 minus alpha minus u. Okay. So if I write the expressions, so take the expression for VD. Vd is root 3 by 2 Vdo. So, if I write alpha in terms of gamma, it is cos 180 degrees minus gamma minus u. See, gamma is just a definition. I mean, gamma is given by 180 degree minus alpha minus u, that is all. Now, why I also said why we defined that. So, there is a purpose for each and every definition. Plus alpha plus u is 180 minus gamma. Plus 30 degrees. So, I can write this as Vd is equal to root 3 by 2 Vdo minus cos gamma plus u plus 30 degrees minus cos gamma minus 30 degrees. Similarly, I try to write the expression for id in terms of gamma instead of alpha. So, if I take id, sorry, id is is by root 3 cos So, can I straight away write the expression? I mean, if you look at the expression for Vd, so you see that there is cos alpha minus 30 in both expressions, cos alpha plus u plus 30. So, I can write this as minus cos gamma plus u plus 30 degrees minus cos gamma minus 30 degrees. Yeah, only difference is this is plus because there is a minus cos alpha plus u plus 30. Now, if you recall, we related this Vd and Id through RC. We defined a commutation resistance RC. So, we can actually try to relate Vd and Id in this case also. See, what we are doing is the case of 3 and 4 valve conduction mode, it is an abnormal operation. So, if I take this expression Vd, so what I am trying to do is, okay, let me instead of, suppose I take this as equation 1, this as equation 2. Okay. So, I use this 1 and 2 to get one more equation, that is Vd is equal to root 3 by 2 Vdo cos alpha minus 30 degrees. Now, what I do is, I replace this cos alpha plus u plus 30 by an expression for that involving Id and Is and alpha from equation 2. So, from equation 2, I get cos alpha plus u plus 30 as cos alpha minus 30 degrees minus root 3 Id by Is. So, this can be written as root 3 Vdo. So, there is cos alpha minus 30, cos alpha minus 30. I think I made a mistake here. This is not root 3, this is root 3 divided by 2. Sorry. So, the 2 gets cancelled. The 2 in the denominator gets cancelled. So, we get root 3 Vdo cos alpha minus 30 degrees minus root 3 into root 3 is 3 Vdo Id by 2 Is. So, what is Vdo by 2 Is? by definition of RC, RC is defined as VDO by 2IS. So, we get VD equal to root 3 VDO cos alpha minus 30 degrees minus 3 times RCID, because VDO by 2IS is given a notation RC. RC is just a notation for VDO by 2IS, that is all. So, we have these two equations. The first equation relates VD, VDO, gamma and u. The second equation relates ID, IS, gamma and u. Now, I can write the first equation, that is this equation, as VD is equal to root 3 by 2 VDO into minus cos gamma minus 30 degrees. Now, the second term on the right hand side has minus cos gamma plus u plus 30 degrees. So, I use the next equation to eliminate cos gamma plus u plus 30 degrees. So, if I do that, I get plus root 3 ID by IS minus cos gamma minus 30 degrees. So, if I simplify this, I get root 3 VDO cos gamma minus 30 degrees with a negative sign. So, minus root 3 VDO cos gamma minus 30 degrees plus 3 VDO by 2 IS ID. So, I can write this as VD is equal to minus root 3 VDO cos gamma minus 30 degrees plus 3 times, we have defined a quantity RC, which is VDO by 2 IS. So, this is 3 RC ID. So, this is an equation that relates VD, VDO, RC and ID and gamma. These are the equations for the abnormal operation corresponding to 3 and 4 valve conduction mode. Okay. Now, there is one thing about the range of alpha that is possible with for this abnormal operation. Say, in the case of normal operation, that is 2 and 3 valve conduction mode, we said that alpha can take any value greater than 0. Now, let us see whether that is possible for abnormal operation. Okay. So, we are still continuing our discussion on the abnormal operation. Okay. So, if I take voltage across valve 3, when valves 6, see when valve 3 is turned on, 6, 1, 2 are already conducting for this abnormal operation. So, valves 6, 1, 2 are conducting. Now, what is this voltage when across valve 3 when 6, 1, 2 are conducting? So, one has to look at the circuit. Okay, I mean, let me draw the circuit. So, this is a constant current ID, EA, EB, EC, L, valves 1, 3, 5, valves 4, 6, 2. So, this is VD. So, 6, 1 and 2 are conducting. What is the voltage across valve 3? Yeah, see, in the table we did not actually get the expression for voltage across valve 3, we got the expression for voltage across valve 1. Again, for getting voltage across valve 1, we used VD, because VD we had already got. So, it is better to write it in terms of VD, and we already know what is VD, we know the expression for VD. So, what is it in terms of VD? Voltage across valve 3 when valves 6, 1, 2 are conducting, minus VD. So, it is minus VD. Now, when 6, 1, 2 are conducting, what is VD? That we can make out from the table. 3 by 2 A. So, minus VD is minus 3 by 2 A. Okay. Now, substitute the expression for EA. What is EA? EA is root 2 by 3 V sin omega OT plus 150. So, it is minus 3 by 2 root 2 by 3 V sin omega OT plus 150 degrees. Of course, I can better to write this as root 3 by 2 V sin omega OT minus 30. I have written just minus sin omega OT plus 150 as sin omega OT minus 30. So, this is the voltage across valve 3 when valve 6, 1, 2 are conducting. So, that means if I want to turn on valve 3, so the voltage across valve 3 is given by this expression. So, what is the inference? I gave a hint, we are talking about the range of alpha. So, can alpha take a value say 10 degrees, 5 degrees? What is alpha? Alpha is the instant at which valve 3 is turned on. So, it should be greater than 30. See, when you want to turn on a valve, first of all it should be forward biased. So, the voltage across valve 3 will not be negative, will not be positive before omega OT less than 30. So, this actually implies alpha should be greater than 30 degrees. See, there is no point in turning on a valve when it is not forward biased. If it is reverse biased, it won't turn on. Okay. So, if you want to turn on a valve and make it allow it to conduct current, then it should be forward biased. So, it will be forward biased only when omega OT is greater than 30. So, alpha should be greater than 30.